Welcome to Excel 2013 Statistical Analysis video number 63. Hey, if you want to download the PDF or the Excel file, and here's the name of the file, Chapter 10, you can click on the link below the video. Hey, we're going to start Chapter 10 over here in the PDFs. Now, we're going to talk inference, and inference for us means confidence intervals and hypothesis testing. We're not going to do it for one sample mean. Now we're going to do it about the difference between two population means. And we'll also talk about experimental design and then analysis of variance for what you want to do when you want to compare more than two sample means. Now let's go back and remind ourselves what we did in Chapter 8. Confidence intervals. Remember, we built these intervals and we said, hey, we're 95% sure that the interval based off of a sample contains our population mean. We ran a 5% chance that we might build an interval that didn't contain the population mean. Now, that was Chapter 8. Those were confidence intervals. Chapter 9, hypothesis testing. Remember, it was one population mean. We set up our tests. We had our fail to reject region, our reject the null hypothesis and accept the alternative on either side. This is for a two-tailed test. And we said something like, hey, here's our critical values, and we're 95% sure that X bar lies between these two critical values. The 5% risk here in hypothesis testing was that we might reject the original null hypothesis and accept the alternative even when the null hypothesis was true. Now, in both cases, Chapter 8 and Chapter 9, we did Z and T. Z, that's when we know sigma, population standard deviation. When we don't know sigma, that's the population standard deviation, then we use T. But here's Chapter 10. We're going to do both hypothesis testing and confidence intervals for the difference between two population means. Now again, at the end of the chapter, we'll do analysis of variance when we have more than two. But here's an example. If we're interested in whether two population means are different, hey, we have a sample mean income calculation for the city of Bradford, and we got $38,010. We also had the mean income of Kane. That sample mean was $35,006. Now there's the difference. So the question is this difference due to chance or is it a real difference, meaning statistically significant? Now let's go to our next page. Another example, and we'll do both of these examples here. We have a sample mean for imported compact cars. And we went out and got a sample and calculated the miles per gallon, 36.25. Then we did the same for domestic and got 33.82 as a mean for our miles per gallon. So the difference is 2.69 miles per gallon. So the question is this a statistically significant difference, which means we might conclude with reasonable evidence that one MPG might be higher than the other? Or is it not statistically significant difference? Now, the actual calculation we do, hey, we'll just take the first X bar and the second X bar. And we'll always be careful to define one as the first and one as the second. And then always make the calculation 1 minus 2. But that calculation, the difference, that's this right here, that's the point estimate of the population difference. So remember, sampling error, sometimes if it's within the region, we're going to go, hey, that's just a sampling error. But if it gets past some hurdle, then our estimation, our point estimate of our population difference will become too big, and we'll say, hey, there is a difference. But just as we did in earlier chapters when we took a single X bar and compared it against the sampling distribution of X bar, what we'd like to do in this chapter is take, hey, Xbar1 minus Xbar2 and compare it against the sampling distribution of Xbar1 minus Xbar2? Yes, and we'll look at an example in this video where we actually create the entire distribution just like we did back in Chapter 7 and see if our formulas really make sense. And once we do that, once we establish that we can use the sampling distribution of Xbar minus Xbar, then we can use Z or T depending on whether we know sigma. But before we do that, let's go back and think about Chapter 7. Now remember back in Chapter 7, we had the sampling distribution of Xbar. This is the probability distribution of all the possible values of Xbar. Now remember, Xbar was the random variable. And we saw a couple of interesting things back in Chapter 7. We noticed that if it was possible to list every single Xbar, meaning the sum of all possible Xbars, and then divide by the count, it was exactly equal to the population mean. So that was very useful because that meant now we could just go take a sample and compare it against our sampling distribution of Xbar. We want to try and do the same thing over here. Here in this chapter, we're going to have a sampling distribution of Xbar1 minus Xbar2. It's the probability distribution of all possible values for the differences, right? The actual random variable will be Xbar1 minus Xbar2. But watch this. We're going to do this in just a moment. We're going to calculate every possible difference. And we're going to add them all up and divide by the count. And we're going to discover that the expected value for Xbar1 minus Xbar2 is exactly equal to our population difference, mu1 minus mu2. Now remember, this is just a formula we're given, but we're actually going to try and do it. We're going to list every single one and see if this is true. Not only that, but we also talked about the standard deviation of the sampling distribution of Xbar. This is the formula that we use. And we saw when we actually had every single Xbar, we could calculate this and see that, yes, it was exactly equal to the standard deviation of the sampling distribution of Xbar. Over here, we're going to try and do the same thing. We're going to list every single difference and calculate standard deviation of sampling distribution of Xbar1 minus Xbar2, also, of course, known as standard error. This is our formula, and we'll try and see that, yes, this formula is a lot more complicated than this one, but it will calculate exactly what we want. Now, remember, that big N minus little n divided by big N minus 1 square root for both of these, those are correction factors. In this chapter, they never even do it. They just assume that the original population is big enough that we're never going to have to do it. We have a trigger to determine when we have to use the correction factor. Little n divide by big N. If it's less than or equal to 0.05, then we don't have to use it. Now, when we go ahead and create this and prove that all the formulas kind of work for us, we're going to have to use the correction factor just because our sample size is too small. Now, on the next page, here's what we're ultimately going to be able to do. We're just going to go out and take a difference and compare it to our normal curve, because we'll prove that the sampling distribution of Xbar1 minus Xbar2 can be used. If we find the differences is in here, and the middle part, the mu, will be 0, right? The difference is 0. If we get a sampling difference that's out here, then we're going to say, hey, there probably is a real difference. Now, before we jump over to Excel and prove to ourselves that the sampling distribution of the differences kind of makes sense, here's what we're going to try and prove. That the original population difference is exactly equal to the expected Xbar1 minus Xbar2, or the mean of all the sampling differences. We also will see that the sampling distribution of Xbar1 minus Xbar2 tends to be symmetrical, that there's less variation, and that this formula works. All right, let's jump over to Excel. Now, here's the example we're going to use. Town 1 sample of incomes, town 2 sample of incomes. Now, why are the samples so small? Because once we go through all of our calculations and then get the list to the actual list of the differences, just from these teeny populations, it's huge. But no problem. It'll prove our point. Now, let's think back to Chapter 7. And notice right here I have the 2 videos. We already did all of these calculations to go from one single sample sample to list every single possible combinations, all the averages, and then we did some calculations to prove that our formulas work. Now I'm going to go through just a few of these calculations from video 43 and 44 just to remind us, and then make a parallel to when we do similar calculations for the differences. Now here it is, town 1. Well, the n, that's the population size, is 5. We're going to take a sample size of 2. So each one of these samples is 2. The combinations, we use the combine function, right? So the total number of combinations. Now, when I listed these, notice, if I'm going to list every possible combination, I take the first one matched up against boom, 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 boom. And then I take the second one matched up, boom, boom, boom. So that's what I did here. Once I did that, I calculated the average. Now, drum roll. If we take the average of all of these, it better be exactly equal to the mean of the population. So equals average. Oh, yeah, the mean of all the X bars and enter. So it's
410.
So it's exactly 40,410. When we take the mean of the population, boom. The beauty of this, of course, is because these are the same, we can take any particular sample mean we get, compare it against the sampling distribution of X bar, and use our original population mean as the expected X bar. Now, the next thing we did in Chapter 7 was we had a formula for standard error. And so we wanted to see if this formula kind of made sense. Now, we're going to have to use this correction factor because our big N and little n are very small. And if we do this division, 2 divided by 5, that's 40%. So that's much bigger than 0.05. So that means we have to use our correction factor. Now, the original population sigma, that's standard deviation, equals stdev dot p. We simply go bloop. And in some of our problems, we're given this population standard deviation. And when we're given that, we're allowed to use this formula to estimate the standard deviation for this distribution. Now, we have this distribution, so we can go ahead and prove to ourselves equals stde, and we have to use p. And the reason why is, yes, these are all samples, but this is a list of every single possible sample, so it actually is a population. Now, that answer right there, that's the number we have to estimate with this formula. This is the one that we almost never can calculate because we never have our entire distribution of X bars. So let's see if this formula they gave us back in Chapter 7 works. We're going to take, hey, what was given to us, population standard deviation, divided by the square root of n. That's our 2. Now, that would not be the right number because our sample sizes are so small. So we have to run our correction factor. Square root, parentheses, we're going to take big N minus little n, close parentheses, divided by big N minus 1, close parentheses, and lo and behold, when I hit enter, boom. Now, that's what we did back in Chapter 7, right? We went through the process of listing every single possible sample combination, the averages, prove that the means are the same, and even prove that our formula works. Now, before we jump into our sampling distribution of differences, I want to do one calculation that we're going to need later. The population variance, and they'll use the symbol sigma squared sub 1. So this is the first population, and so the variance is, oh, I already have my population standard deviation, so I simply square it. So we have that, and we have that over here also. Now, I already did all of the calculations for town 2, but now let's talk about complete listing of all the differences between these two sampling distributions of X bar. Now, imagine if we were going to do this. We'd have to take the very first X bar and subtract every single one of those. Then we'd have to go to the next one. Remember, our goal is to list every possible difference between these two sets of X bars. So then I take that, and there's 10 of them, so I have to list that 10 times and list every single one of those. And I have to go through and do every single one matched up with all 10 of these. Now, to figure out the total number, it's not a combination. We simply do, oh, yeah, 10, because there's 10 of those, times 10 of these. Now, I went ahead and did this. Notice that, boom, there's exactly 10 of the very first X bar from population 1. matched it up against every single one of the X bars from population 2. Then I went to the next one. Boom, there it is. I listed it 10 times. Oh, my heavens, that sounds like torture. And then listed every single one of those booms. Now, I actually used formulas for these control down arrow, way beyond the scope of this class. But if you're interested and you want to watch this, I just used index, and actually that number increments the numbers 1, 1, 1, 1, 1, 1 10 times, and then 2, 2, 2, 2, 2 10 times. And this one lists, index isn't a formula we use in this class. It's a type of lookup function. But this number right here lists the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's a video there all about that. Beyond the scope of our class, but you get the idea. All of the samples listed from the first one matched up against all the second samples. Now we can calculate the difference, and it's important. I'm going to take the first one minus the second one. That's one possible difference. That means if we had gone out and got random samples and got these two samples from town 1 and town 2, we would have ended up with that difference. But when I double click and send it down, I list every single one of the differences. And of course, some of them are going to be negative, some of them are going to be positive. All right, now, what do we do with that? Well, we're basically going to do the same thing we did back in Chapter 7. But if we're going to compare these two, we're also going to have to do the same thing for the actual population difference, mu1 minus mu2. So I did the same thing, listed all of these many times. That's every single possible population difference. Remember, there was 5 in the first, 5 in the second. That's why I would list the first one 5 times matched up against all 5 of the second population. All right, so now we can calculate the difference. I'm making sure that I get the first one minus the second one. Control-Enter, and double-click and send it down. Now we have a list of all of the Xbar differences and all the population differences. Let's do number 1. Let's calculate the mean of all the sample differences. So that's all of these. All right, you ready? Expected value of Xbar1 minus Xbar2. Click in the top cell, Control-Shift-Down arrow. Shift-Enter to put it in the cell and pop back up. All right, and here's the drum roll. Equals average. I want to calculate the average of all the population differences. No way. Control-Enter. They're exactly the same. Now I want to go back over to our PDFs. Notice, that's what we were trying to prove. The difference between population means mu sub 1 minus mu sub 2 equals expected value of X bar sub 1 X bar sub 2, or the mean of all the sample differences. One of the reasons this will be so convenient is because if we assume that we're trying to check if two population means are the same, then this difference would be 0. So if we go out and get a difference using samples, we can hopefully compare it against our sampling distribution of Xbar. And if it's far away from 0, then we say, yes, there is a difference. Now let's go back over to, and we can actually do this another way. Notice mu of the population minus mu of the population. So here I could say equals average, and I'm going to scroll way over. And now I'm going to build my formula up here in the formula bar. I'm going to say, oh, here's the original population, average of all that minus the average of this population. And guess what? When I hit Enter and scroll over, it's exactly the same. We could do the same actually right here. Remember, this was calculating the differences. You could actually still do it a third way. You could say the average of all of those minus the average of all those, although this one's kind of silly here, but they're all the same. Not only can we do that for the population, but remember, this is taking just the average of every single possible difference from all of the possible differences from our samples. If we did equals average of the original X bars, all of those, close parentheses, and I'm building my formula up here, minus average, close parentheses, and Enter. And we get exactly the same thing. And we could get silly here. And of course, it would have to be, if we calculated the average, and I'm building my formula up here, of the actual 2 towns, every single number listed there, we'd get exactly the same thing also. Now, the next thing we'd like to do after seeing that mean of all the sampling differences is equal to the population difference, we'd like to talk about the variation difference between these and the shape of the data. Now, earlier in the class, we built upper and lower and labels, and then did countifs to count between a lower and upper. I did that for the population differences. I also did that for the sample differences. So now I will simply copy these formulas, and the charts are already created. We've made lots of charts and formulas like this earlier in the class. And lo and behold, here's the population, and here's that sampling distribution of Xbar, or just every single difference that we took from our two samples. The first thing we can notice is the distribution. This definitely doesn't look like a bell-shaped or symmetrical distribution. But once we start plotting all of the differences from our Xbars, then the distribution tends to be symmetrical. And you remember what we said earlier in the class is if you plot something like this and it looks or it's close to symmetrical, then using the normal distribution functions as an estimation is an acceptable tool. The second thing we want to notice is the variation. So it looks like the upper category is minus 50K to minus 45K, all the way up to 55 to 60K. Remember, these are differences, right? Down here, it looks like the upper limit is minus 35K, and the upper limit here is 45. So variation is smaller in our sampling distribution of Xbar minus Xbar. If we go over to our PDFs, there we go. Number 2, sampling distribution of Xbar minus Xbar. Xbar1 minus Xbar2 tends to be symmetrical. And there's less variation in the sampling distribution of the sampling differences than there is in the original population difference distribution. Now, the final thing we want to look at is this formula right here. We want to prove that this actually makes sense. Now, again, just as we did back in Chapter 7, we have the luxury of calculating our standard deviation for the sampling distribution of differences a few different ways. We have all of our differences, so we can do it straight from here. And then we'll do our formula and see that it works. Now, the first thing is sample size n and population size. So we'll calculate sample size n. And I got to show you a little trick here that we're going to have to use, because a lot of these formulas, we're actually going to have to go way up to the upper corner of the spreadsheet. So watch this. Equals and control home jumps to cell A1. Now notice the dancing answer dancing, and that means the cell reference is still in edit mode. So now I'm simply going to click on the N and then enter. Now I'm all the way back down here. I want to do the same thing for population size. Equals control home. The nice thing about that is it's still in edit mode. It jumps us all the way up near where we want and moves the screen. And now I want big N and enter. Scroll over here. Now, if we calculate our trigger, n divided by big N, it's clearly gigantic compared to 0.05. So when we do our formula, which here's our formula. This is the formula that we're going to have to use in our calculations. And we want to prove that this formula calculates the right number given population variance and our sample size straight from our differences. So let's just go ahead. Here's the standard deviation of the sampling distribution of Xbar minus Xbar equals STDEV. And guess what? We're using population because, yes, these are all sampling differences, but it's every single one. So this is a population. Click on the top cell, Control-Shift, down arrow, and Shift-Enter. All right, that's the number. The only reason we can calculate is because we have all the differences. Now let's do this formula and see if we get the exact same answer. Equals square root. And it looks like we take variance divided by sample size 1. And here's where the 1s and the 2s and the numbering of our samples and populations is so important. We got to get it right. So you ready? I need variance from the first divided by sample size of the first. Control home. All I did was jump up here. Now I'm going to get the variance from the first. See that sub 1 right there? Now, notice the formula is forming up in the formula bar. Division symbol, and now I'm going to click on sample size 1. Now I'm going to type a plus. Notice the formula emerging in the formula bar. Now I click on variance. I can see it up there. Divide by, and our sample size 2. Close parentheses. I can see the formula up here. I'm going to Control Enter. Now that just kept the cell, that put the formula in the cell and kept it selected. But I'm going to scroll over here, F2, because now we need to do our correction factor. Times and square root, in parentheses, big N minus little n, close parentheses, divided by big N minus 1, close parentheses, close parentheses. And I'm looking right here. I missed a parentheses because I have a color on the end, and it should be black. So I'm going to look right over here. And sure enough, I forgot a parentheses because I need that division to happen before that subtraction. So there we go. Now, I was watching closely there. That's why they color code it that way. The black one's got to be at the end. And watch this when I Control Enter. Boom, they're exactly equal. So yes, we plotted every single difference, calculated the standard deviation for that distribution, and then we have our formula they're going to give us in our book, and we went ahead and calculated it, and sure enough, it seems to be working. All right, now in this video, we just played around with our sampling distribution of differences, Xbar1 minus Xbar2. We also created the entire distribution of population differences. We went ahead and saw that the mean of all of the sampling differences, or expected Xbar1 minus Xbar2, is exactly equal to mu1 minus mu2. We then saw with our charts, if we plot all of the sampling differences, it tends to be symmetrical, and there's less variation. And finally, we saw that this formula we're going to use right here is going to work for us. All right, next video, we'll start with confidence interval when sigma is known. All right, we'll see you next video.